Welcome to this developer blog. Today we're taking a look at Sahara Text Lens, a data-driven text analysis tool built in Haskell. We'll walk through the core code and main functions, and then run the application with a series of examples. Bookmarks are included in the video, so you can jump straight to the sections you're most interested in. The entry point is main.hs, which renders the main menu, processes user input, and outputs the results. The key purposes of this application are summarizing web pages, including both static and JavaScript rendered content, ranking sentences using word and phrase scoring, generating word bubbles from weighted keywords, analyzing sentiment with configurable dictionaries, using JSON-driven configuration for ranking and sentiment analysis. Each of these features is built from small, focused functions, making the logic easy to test and edit in the future. The menu has a number of options. Enter text to analyze, allowing you to type freely and view the full analysis. Web page summarization, offered in two forms, one using Haskell-only fetching and another using Playwright-powered, JavaScript-rendered page retrieval via Node.js. The final two options are listing ranking data, showing the weighted words and phrases, and the About page for rules and examples. The About page is split into three parts. The first is Word Bubble, a quick snapshot of the dominant themes in the text. It highlights the most important ranked words based on your word ranking configuration. Words are sorted by frequency, and brighter colors indicate higher ranked terms. Next is the Sentiment Analysis System, which identifies the emotional tone of the text. This is fully driven by your own definitions, using a collection of positive and negative words, along with intensifiers and negators to shape the final sentiment score. The final section explains how the system identifies the most meaningful sentences. It uses your word and phrase rankings, combining them to produce a weighted score that highlights the strongest, most relevant lines in the text. The TextAnalysis Module holds all the core logic, from simple word and sentence counts to the more advanced process of identifying the top sentences based on your ranking data. Each component is broken down into small, focused parts and then composed together when needed. It also handles all formatting, such as wrapping matched phrases in cyan square brackets and highlighting ranked words in yellow. The logic for both the word bubble and sentiment analysis features is implemented here as well. Haskell's strengths made this work easier. Its expressive data handling capabilities and powerful functional patterns supported the project extremely well. The WebFetch module extracts readable text from HTML using a series of cleanup steps. These include parsing the HTML into tag soup tags, removing all script blocks, collecting only visible text nodes, inserting spaces between text nodes to prevent words from running together, stripping out JSON like noise and normalizing all whitespace down to single spaces. The WebFetch Advanced module is used to retrieve fully rendered HTML using a Playwright script running through Node.js with a Chromium browser. Once the page is fetched, it applies the same cleanup steps used in the standard WebFetch module. This approach makes it possible to read and process more complex websites, especially those that rely heavily on client-side scripts. This JavaScript file tells Playwright where to find the portable Chromium browser. It loads the required libraries and reads the URL passed in from the Haskell program. The PhraseRankings module loads the JSON file containing the phrase and rank fields. The WordRankings module loads the JSON file containing the word and rank fields. The SentimentConfig Module loads the JSON file containing the lists of positive words, negative words, intensifiers, and negators. To highlight the rules in use, I created a simple diagram that shows the main parts of the application. All of the core logic and rules are implemented in the TextAnalysis Module. The ListRankings Module lists all ranking data used in the application, from the word and phrase rankings to the sentiment configuration. It also detects any duplicates within these lists and highlights them. Some color formatting was added to break up the text and interface, making the application more user-friendly. The TextInput module handles user input, ensuring that an empty line correctly marks the end of the input block. As the project grew, I added tests for each new feature. This made it easier to see how each module behaved with different types of data, including mocked HTML pages. This next part demonstrates the application, walking through each of its features and comparing the results from the two web page fetching methods, the Haskell approach and the Playwright-based JavaScript approach. Option 1 lets you enter free text on a single line. It's a quick way to see immediate results and check the score the system assigns to your sentence. Option 2 fetches a web page using the Haskell-based approach. This works well for all standard, non-script heavy pages. You can see the ranked phrases and words highlighted in the output, showing how each one contributes to the weighted score for the top sentences. Option 3 fetches a web page using the Playwright-based JavaScript approach. This method is better at handling pages that rely heavily on client-side scripting. Comparing the results from Option 2 and Option 3, you'll notice some clear differences. The number of sentences and word counts vary between the two methods, depending on which parts of the web page each approach is able to capture. What I found is that the more data you provide, the better and more accurate the results become. The application includes checks to ensure that all required files are available before it runs, since it relies on JSON data files and uses Node.js for Option 3. It also checks whether Node.js is available and whether the required Playwright libraries are installed. Option 4 lists all the data used by the application, providing a quick way to view the JSON files without opening them directly. It also highlights any duplicates it finds. Option 5 is the About page of the application. It includes all the rules, along with examples that show exactly how the weighted scores are calculated. The final part of the video walks through tests on a range of different websites and reviews the results. We look at several IT-related sites and try both Option 2 and Option 3 to compare how each method performs. You can use the bookmarks to jump directly to each test. Overall, this was an interesting project and my first real exploration of Haskell. The key was building the application from small, focused functions. Haskell's flexible data analysis capabilities worked well here, along with its simplicity in handling data and supporting easy testing. I'll leave you with the rest of the video. Thank you for watching.
Thank you.